We are recording now. So take out that 1.3a homework. Again, folks at home, make sure you just drop your name to the chat so I know that you're here. And let me know if you have trouble seeing anything. I can, you know what I'll do? While I'm over here, let me share my screen on this one. Present my screen, this one. So everybody at home, you can just kind of pick the window that you like. But this is the one that's going to be recording. Okay. So take a look. Let me know how you did, how you feel. And something that I'd like to see you start doing if you haven't been doing it is what I just did in the top left-hand corner. Please write your name and the date that you're doing it on all of your homework. Not the date it's due, but the date you actually get it done. Okay. So I did this yesterday. So that's why it says 9/7. Okay. And so 29, 31, 33, and 40 all kind of had similar ideas. 40 was just the approximation, maybe potentially, of your relative mins and maxes. But 29, 31, and 33, increasing intervals, decreasing and constant if you had any, and then any relative or global extreme. So take a look, see how you did. If you draw yourself a little sketch of these things when you're doing your work, it's never a bad idea. But that's up to you. That's up to you. I'm going to show you in the calculator just kind of the graphs of them so we can check them out. And I also wanted to show you something in the calculator that maybe you didn't know about. But I'll give you a chance to check them first. If you're at home, do the same thing. And if you haven't submitted yet, get that done some point today. It's just good practice. We probably won't practice this again past this homework. For those constant intervals for 29 and 31, there weren't any. They either were always going up or always going down in some space. So you can write the word none. I forget what I've shown to some classes, what I haven't shown to others. It's called the empty set. Okay, the set of nothing. There is none. So you can write it like that too. Either one's fine. The word none is enough. NA is fine. Whatever works for you. But I like that empty set. This is fancy. I like that. Okay, let me show you those graphs and show you kind of what happens. Let's hide you and go like this. Okay, so there's all four of them, all in one spot. What's that x to the 2/3? The fractional exponents. I might have said it, I might not have. I had to say it today to everybody, so I'm just going to repeat myself in case I have. Do you know what exponents that are written as fractions mean? Ooh, good. Okay, nice. I'm glad you don't know. Okay, they have two parts to them, obviously the top and the bottom. And each of them represents something different. Okay, the 2 versus the 3. Okay, the 2 is whatever your power is, so like x squared in this case, and then the 3 is the root. Okay, so it's always going to be power over root. Because maybe we want to do both. I don't want to just do x squared or just do the cube root. Maybe I want to do the cube root of, in this case, x squared. Okay. Everything else you should recognize, but I want to make sure you've seen that. Okay, so power over root, easy way to remember that. And there's some funky looking graphs for sure. I'm gonna get rid of that so we can look at it. If I like zoom standard or just press graph, it's gonna graph all four of them at the same time. It's kind of nice to have all of your graphs in one place, but I don't always want to look at them all at once. And so it's something you can do if you see you're working through a couple different examples all at once, without having to like erase them and write them over and over and over and over again. Did you know you can turn the graphs on and off? You see how these equal signs, black writing, white background, but these are the opposite? If you scroll left, like I'm blinking on that X right now, you can scroll left onto the equal sign, and by pressing enter, you can turn it off. Now I want to keep that one on. Let's say we want to look at the first one. Maybe I want to like save all of these equations, but I don't want to look at them. I can just go to the equal sign, press enter to turn it off. And now when I graph, I'm only going to look at the first one. The other ones are still sitting there waiting for me when I'm ready in y equals, but I only want to look at this one, which is really nice. Okay, so you don't have to like delete and rewrite to be able to kind of mess around with multiple equations at a time. And so there you go. Negative infinity to 0, decreasing 0 to infinity. Of course, always open intervals, right? Exclusive intervals. So increasing 0 to infinity, decreasing negative infinity to 0, and then no constant intervals. And then you really only had one minimum in the whole thing. So it was the global and the relative at 0, 0, and there was no max. Stop me if you have questions. Now I'm going to turn this one off, and I'm going to turn this one on. X times x plus 3, square root of that. Kind of looks like that. Okay. And so decreasing from negative 3 to negative 2. Right? Increasing from negative 2 to infinity. There was no constant interval, and then you still had just that one global / relative minimum sitting at that spot. And you could do that test, right? You could do second calc minimum. Got to scroll far enough to get left, far enough to be right, press enter, and perfect, right? Negative 2, negative 2. So we know that that one's good. There's no rounding necessary there. That one looks good. Turn this one off and this one on. This is a good one. A couple different absolute value ones. Okay, this one finally gave us a constant interval, which is why I picked it. But increasing 1 to infinity, decreasing negative infinity to negative 1, and then constant in between. But again, always, right? Open intervals. Don't include those endpoints, because at that moment, you're not going up anymore, you're not going down, okay? And I say that there weren't any extrema, because you have that long string of minima, and that's not really, there's not just one. So I left it like that, okay? Questions on those first three? Those are pretty straightforward. 40 was a little different. I just want to take a second to talk about it. Okay, so let's look at that. Then we'll finish up 1.3. All right, so turn that one on, turn this one off. Now just take a look at that equation first. Can we plug in any number in for x that we want and get a real number back? Like, can I plug in 0? 0 times the square root of 4, so 0 times 2 is 0. Okay, can I plug in 1? 2, 3, negative a million? Because 4 minus negative a million would be 1,000,004, right? What about the number 5? Can I plug in 5 and get a real number back? Why not? Can't do it, right? Not in the real number system. Yeah, we'll talk complex, but I want to graph real numbers. So negative 5, 5, 6, 7, numbers bigger than that, even like 4.1, 4.001. None of those are going to be good, which is why this graph stops. Right? There isn't in this infinite domain because we've got that square root. So we just want to be careful with that. And so this question just asked, okay, where's your min and where's your max? Do you have a minimum? Do you have a maximum? And we said, okay, I can plug in negative a million. This graph is going to keep going that way. Right? So there is no global minimum, but they weren't asking for that. They just wanted relative. Right? If you read the question for number 40, right? Use a graphing utility. That's their way of saying use a calculator or some sort of graphing calculator, Desmos, whatever, and approximate any relative minimum or maximum values of the function. So that's what we're going to do. We're going to try to look at this and see where the relative mins and maxes might be. So is there a relative minimum anywhere? Someplace that in the space nearby, it's going to be the lowest point? Yeah. Right, but like we said, if we plugged in 4, we were going to get 0. And so I think I showed this to you, and hopefully I did. Like, there's not a perfect graph that the calculator can handle because it's getting so close to 0 that it's going down really, really quickly. So this graph should actually continue on to here. So be really careful with what you assume from the graph that your table, that your table will tell you is actually happening at 4. Okay, now everything past that is just going to spit out an error, right? Because it can't do it anymore. But there is a point at 4, 0. It's just not going to draw it very well when you're in zoom standard. One, you're too far away, so the pixels are all messed up, okay? And so what I like to do sometimes, there's a great option if you're kind of close to the origin. If you want things to happen at nice increments, you can always just zoom in, but you'd have to zoom into a certain spot. It's going to get you 4 times closer. That might be too close. Zoom decimal is a good one. So zoom number 4 will just get you a little bit closer. And look, yeah, it's not perfect, but there actually is, if you were close enough, there actually is a point sitting there. Okay, zoom decimal is awesome. That's a little bit more indicative of what this looks like. Okay, so that looks like a relative min. Call it 4, 0, right? In the space nearby. But what about this point up here? Did that fall at a nice value right there? Or a nice value right there necessarily? Kind of hard to tell. And I don't want to guess. I don't want to assume. I want to just let the calculator do as much of this work as I can. And so last time we saw it, I can find that relative minimum. All right, well, I can find a relative max too. Second calc, I want to pick maximum because we're looking for relative max. When I do my left bound, right bound, I like to get a little closer. So let's say left bound, cool. Right bound, close enough. Enter, and then it gives me this. Can you see those decimals there? Peek around if you can. 2.666666678. Do you think that's exact? Probably not, right? What about the 3.0792 whatever? Probably going to keep going, right? Now, you could get closer and closer and closer. You could zoom in, and I'm going to pick my center to actually be that point rather than anywhere else. It's going to get me 4 times closer, and I could do it again. Now, I think we had like 2.6666. I think there were 5 of them, and then 7, 8. Let's see what happens again. All right, make sure I'm left enough. That's definitely left enough. See that little plateau there. Right enough, and enter. Oh, well, look what your maximum x value did. It's different. 2.66, there's 5 6s again, but instead of 7, 8, now it's 4, 3. The y value didn't change though. And you could do this over and over and over and over and over and over again. What do you think that x value probably actually is? Probably, right? Now, can we know for sure? Definitely not. So when we approximate, it's okay to give your best guess, right? Because that's what the calculator is doing. Remember, left bound, right bound, guess. We kind of have to as well. We're going to do our best guess. So when I wrote my answers down for this one, I said, all right, 4, 0, definitely my relative min. But my relative max, I think it's 2.6 repeating, which is 8/3. But I'm not sure because I keep getting closer every time. So I want whoever's reading this to know that I'm just guessing my way through this. And then when I wrote the y value, 3.0792, and it kept going, I have to round. And in here, we are always going to round to 4 decimal places. Always, always, always. You want to know why? Because the AP Calc, AB or BC, wants 3. And if we do more, we're just better. Okay, so always round to 4 decimal places if we need to. Okay? Sweet. All right, moving on. Let's finish this thing up. I think we might have started to talk about this at the end of last time, but let's do it now. Let's talk about our last topic. Yay, 1.3, almost done. Write some stuff down. Take us on the right with something to write on. I just want you to jot down a couple things, and I want to give us time to try this out. My guess is that this is not new, which is wonderful. Okay, so I'm going to keep it short, sweet, lovely. I'm going to be over here a little bit, but as soon as I get away from the board, I'm going to take this one with me so everybody at home can check it out too. But all we're going to talk about, this is going to be the last thing that we do. We are talking, I'm going to give it a name. It is, that's a weird Y, but we're going to leave it. Symmetry. There we go. Symmetry. Graphical and algebraic. Okay. Okay. And there's 3 types. Okay. Let's zoom in. Okay. Graphs can be even, which it says right here. Right? And if a graph is even, it's just symmetric to the y-axis. But there's something, kind of big happening. We'll talk about that in a second. We'll do the graphical side first. I bet you know this, though, which is good. Okay, or functions can be odd. That's when they're symmetric to the origin. So the point 0, 0. This is the line of symmetry. This one has a point of symmetry. It's kind of reflecting yourself either over the line or through that point. Or you look at the last one, well, it's symmetric to the x-axis. Well, that's not a function, so I'm not worried about it. I don't have to worry. Like, don't even bother telling me that it's symmetric about the x-axis because it's not a function, and I don't care about things that aren't functions yet. But it doesn't have to be any of those, right? It could be a function but just not be symmetric. So it's even, or it's odd, or it's just neither, and that's okay. Most functions are probably going to be neither, but we do have some functions that are symmetric to the y-axis. We call those even. Symmetric to the origin, we're going to call those odd, and then symmetric to nothing, like neither of those. So if I don't know, like if I drew, say I drew this graph, super tiny. Like I drew a parabola, but I put it over here. Is that symmetric to the y-axis? Is the line of symmetry right down the middle of that function the actual y-axis? No. Is that symmetric to the origin? So that graph, that blue one with the green axes, that's just neither. It doesn't have functional symmetry. Now, does it have a line that cuts it down the middle? Absolutely, right? I still have some line, let's say like x equals 3 or whatever, goes right through the origin, right? That's a perfect line of symmetry, but it's not symmetric. It doesn't have functional symmetry. Okay, so it could have symmetry, but just not functional symmetry. So I want to make sure we clear the air on that one. Cool. Good? All right, you try it. Here. Try these 4. Tell me what you think. Folks at home, I'm on page 30-something. 35, I think. Yep. On page 35, so if you are at home and you want to look these up and just get a little bit closer, you can. It's just example number 9 in the textbook itself. All you have to do visually, and I really just want you to look at it visually and say, is it even? Is it odd? Or is it neither? Use the figure to determine whether the function is even, odd, or neither. Again, at home, just write your name in the chat so I can take attendance. And you do it too. And I have you guys in my ear, folks at home, so let me know if you have questions. Just unmute yourself. If you can't see, can't hear, can't read, whatever the case may be. And I hope it's easy. I hope you just look at it and you're like, yep, got it, nailed it. Then we'll look at the algebraic side, way more important, but still nice. I like to look at pictures too. It's a nice thing about being a dad. All my books that I get to read now all have pictures in them. It's amazing. Some books even read for you. Like, I don't know if you guys have little siblings, but like they have like Disney princess books, and like it comes with like an e-reader. You just press a button and it reads the story. So I'm there like half asleep on the floor and she's pressing buttons. It's amazing. It works. All right. A, even, odd, neither. Shout it. Even, right? There it is. Line of symmetry. Perfect line of symmetry. Every point is directly across from another one. Okay. What about B? Even, odd, neither. Odd. Because through this, right, this point, that same distance kind of goes right there, right? That same distance across works. What kind of graph is that, by the way? What function is that if it makes that V? Absolute value. Good. What about B? What kind of graph is it if it has that kind of curvature to it? Not straight. It's definitely curved. Huh? Cubic. Good. Yeah. Cubic, right? This is going to be x cubed. I don't know why I wrote those words and then wrote that. Okay, good. What about, I guess it's C, huh? Yeah. Even, odd, neither. Say it again. Neither. Good, right? Does it have some line of symmetry somewhere, though? Absolutely. But does it have functional symmetry? Definitely not. What kind of graph is that? Quadratic. It's going to be some version of x squared. Right? It looks like it got maybe moved over 2 spots. So instead of x squared, let's see if you remember. To the right 2. Nice. Good. Nice. That's why we're not doing 1.4, because that's transformation. Good. Now you proved it to me. Now I feel better. Okay, what about D? Even, odd, neither? Even. Line of symmetry is the y-axis. Good. All right, what's that one? Do the transformation. Let's say it's a down 1. Inside the parentheses, like this one? Outside, -1. Good. Hooray, done. Okay, moving on. How about, all right, we need to be able to test for these, okay? What's in that yellow box? If you think you need to write it down, okay? How to test if a function is even, how to test if it's odd, or how to test if it's neither. They're all the same test, but they have different results, okay? If you want to be able to tell, let's look at me, so I make sure y'all can see. Give me a shout if you can't. How about like there? Okay. The test is always the same. Okay, testing for symmetry. Did you do this part last year too? Okay, good. Okay. So we got to be given some function, and what we want to do is we want to see what happens if we drop in negative x. Okay, I'm going to use something darker, black. Okay. And what we're going to have are 3 possible results. Okay. F of negative x might have given us exactly f of x. Right, you plug in some negative version of all of the same numbers, and I get back the exact same function. Okay. If that happens, if they're exactly the same, then it's even. So no sign switches at all once we simplify. Maybe we get the exact opposite. Every sign switched. Every single one switched sides. If that happens, then it's odd. And if it's not equal to either of them, then it's just neither. If we get something different. Some signs change, but some don't. Let me, I should have, yeah, good. All good? All right. Let's see. Do I want to try it? Let's just make up a couple here. Let's try it. All right. So let's call this number 1. All right. Let's say f of x is x squared minus 3x plus 1. Do it with me. And we just want to take a look at that and say, all right, is this function even, odd, or neither? Now, could we just graph it and look at it? Sure. Right, but they may ask us to prove it algebraically. They may say you have to do it this way. You can't graph it. Or maybe you can, but it's not enough. Prove it to me for sure. Okay, so it's given. So we're good there. Now all I want to do is test this out. So there's the problem given to me. Here comes my work that goes along with it. My job is to change every x to negative x and see what happens. If I get the exact same thing, even. If I get the exact opposite, it's odd. If I get some combination, it's neither. And so right there and right there, I got 2 x's, so I got to change 2 of them. I'm just going to drop in not x anymore, but negative x. Well, what's a negative number times itself? The positive version of that same number times itself. So I can change this back to just x squared. Ooh, nice. Okay, so x squared stayed the same. So far this function's even. All right, but what about negative 3 times negative x? Positive 3x. And then, of course, positive 1 doesn't change. So this term and this term stayed the same from above, but this one switched. I want them to all be the same or all be different. If you get some combination, neither. Now, what kind of graph is this function going to make if it's x squared minus 3x plus 1? What shape? Quadratic, right? So what's the shape of the graph? And we know that those have symmetry. They don't have to have functional symmetry. Okay, good. G of x. X to the 6 minus 3x to the 4th. How about that? Okay, same process, right? Given some function. Now it's g, so I'm going to use g. Change every x that you've got into just negative x. Don't change this thing about anything else, but let's just see what happens. Right? We always just want to kind of simplify. So test this and simplify. All right, well, what's a negative number times itself 6 times? Negative, positive, negative, positive, negative, positive. So back to positive. So I don't need that negative inside there anymore. I can just say it's the same thing as taking x to the 6. Whether it was the positive x or the negative x, you multiply it by itself an even number of times, we're going to get the positive version. So is that still true here? A negative number times itself an even number of times, this part won't change. So this is positive x to the 4th. So negative 3 times positive x to the 4th is negative 3x to the 4th. Is that the exact same thing as you got up here? Then tell me that. Say g of negative x is the exact same thing as g of x. And then we can say the word therefore, like, hey, I've come to a conclusion now. Therefore, g of x is even. But therefore just has way too many letters in it. 9 letters? No way, I'm a mathematician. I'm going to write one symbol that does the job instead. Okay, and so there's a symbol that means therefore. I don't know if you've seen it. Nice. I like this. I like teaching you new stuff. It looks like this. The 3 dots that would make up a small, nice equilateral triangle. Therefore, g of x is even. So I came to some nice answer, and it led me to a conclusion. I just want to say that. So g of negative x is this. Okay, cool. Therefore, g of x is even. Okay, one more. I wonder what this one's going to be. H of x, 2x to the 3rd minus 5x. How about that? You see me? Yeah, nice. So what do I do? The same thing every time. Just drop in negative x and see what happens. 2 times this. And you see, I always use parentheses when I substitute. This way I'm being safe and careful, and I'm making sure that I'm not getting my signs all screwed up, because that's the only thing that matters in this problem is what's the sign? Oh, they're all the same? Cool, even. They're all different? Odd. Some combination, just neither. Negative number times itself 3 times. Positive or negative? Negative. So negative 3x. Negative 2x to the 3rd, because this is negative x cubed times 2, so negative. Negative 5 times negative x, positive 5x. So have all those signs switched from the beginning? Positive to negative, negative to positive. So what I would love to see in this case is you telling me that. I want to see h of negative x is the exact opposite of all of h of x. I want one of these 2 results if you're going to tell me it does have symmetry. Okay, I want to see that. Okay, so if I drop in negative x, I get the exact opposite of what I started with. Therefore, write it, use it, h of x is odd. What's this exponent right here that I'm not bothering to write over the x? 1. Tell me something you know about the number 1 and the number 3 in terms of its parity. It's odd. Parity, even versus odd. Oh, all the exponents are odd? What kind of function was it? 6 and 4. What is the parity of those numbers? That's not a coincidence. If all of your exponents are odd, the function's odd. If all of your exponents are even, the function's going to be even. Okay? The thing we have to watch out for is this is 1x to the 0. Okay? Not really even or odd in terms of what we're dealing with here. Okay? But if you think about it, is 0 divisible by 2? Do you get a number back? And that's okay. And remember what adding or subtracting a number on the outside did? It just shifted it up and down. So if it was even from the beginning, shifting it up or down is not going to change whether the y-axis is that line of symmetry. So you're good there. Good? Okay, try them. ABC. So back to here. Let me scroll up. I'm going to bring you with me just for a second. Hi, folks at home. Math in your pajamas. Lucky. Let me scroll up so the folks in the back can see it. Okay, let's go like this. I don't care if you can see the answer. There we go. Boom. All right, so try this one. Determine algebraically even, odd, or neither. And I'd love to see that last little line telling me how you know for sure. Right? Make a conclusion. Say things that you mean. Okay. And 8:35, 9:25. So we got some time cruising along. Let me see if there's anything else. I will have time to show you one last thing. Again, folks at home, if you have a question, let me know. Folks here, please talk to me. But I'm guessing that this is something you remember. But good practice so that when you see it on our test that we'll take sometime really soon, it'll be ready to go. I don't know what it looks like yet. I really don't. I want to figure out what works. But what I did hear is that other math teachers are dealing a lot with cheating. So we'll see. We'll see how it goes. Because this week's weird because we lost Monday, which is why people that are cohort A are hopefully joining in today and watching the recording, one or the other. And I figured this would be an easy kind of review lesson to do while you guys are getting back from a long weekend. It's gonna snow, and people are stuck at home too. So I figured this would be an easy one to do. Maybe we'll just start kind of getting to some review pretty soon, like for the whole chapter, and then we'll figure out how we want the chapter 1 test to look. So that might be a conversation you and I have on Thursday. What do we want this thing to look like? How are we going to best get this done in a way that gives everybody an equal shot? That's the thing that matters most to me, is that everybody has an equal shot to do well. And in about one moment, I'll jot down some answers, and then I'll show you the last little thing. And then realistically, we're just about done. We really are. We're getting to that point where we've done everything that we needed to in I would say a mostly review chapter, right? Some of the notation might be new, but most of the concepts hopefully aren't, and that's on purpose to get you going. Like I said, I think the pre-calc semester is faster but easier. We do more, but you've seen most of it. Calculus, we slow down and we do brand new things, and it just feels harder because you're learning brand new stuff. Okay, good. Looks like you guys are finishing up. I'm just going to write down my work. You tell me You agree. So I'll separate that. Switch colors. And then switch colors. So I like to do that. There's something that I didn't do in that example 3 there that might be something you like to do. Factor that negative out and make sure what's inside is exactly what you started with. That's really good. Now you could probably just look at this one in blue and say, yeah, every sign switched. Okay, I'm good with that. It's enough for me. This is you talking. Now I can say, sounds good. I feel good. Therefore, I gotta say one thing first. No, don't delete it all. Just some of it. So G, too fast. G of negative x is exactly negative G of x, right? Yeah. Therefore, G of x is odd. And if I was going to box something, I'd box it all. I'm cool with you just boxing the therefore part too, right? G of x is odd because that's the solution. That's kind of the conclusion that we've come to. But either way, that one's good. Good with that one? Okay, so I like that last little line here in red. If you haven't done that, you can try to do that. H of negative x squared plus 1, which is x squared plus 1. Okay, and then cool. So, not G. H of negative x is the same as h of x. Therefore, h of x is even. And hey, look, all odd exponents, all even exponents. Okay, and then f negative x. I like that one line of substitution. I like us, not plus. I like us to kind of take our time and show that one step of substitution, and the rest of the arithmetic, the algebra, can happen kind of quickly from there if you want. Okay. And if you really wanted to get all super technical and go crazy, you could say f of negative x is not equal to f of x, and it's not equal to f of a negative f of x. Okay. Therefore, f of x is neither? Like, neither what? I don't know. I would say therefore, that's a terrible triangle. Oh gosh. Oh man. Therefore, nice equilateral. F of x has no functional symmetry. If you really wanted to say something really pretty and nice, I know I'm going sideways here, and I'm going to stop right there because I'm out of space. You can say that. That's cool. Good?
Mr. Rosengren?
Yes, question from home.
Yes, sorry. Do you have to put both f of x and negative f of x? Like for if the function is not symmetrical?
So the question at home is for this last one. If we find that the function doesn't have symmetry, do we have to write both of those? That f of negative x doesn't equal f of x, and that it also doesn't equal negative f of x? I think the answer to that question is yes. If you want to prove to me, or whoever's reading it, that your function doesn't have functional symmetry, you have to tell me that it's not even and that it's not odd. So say both. Yeah.
Okay, thank you.
Good question. You're welcome. Any other questions? Good. Okay. Last thing, and then we're out of here. Let's bring this back. I forget if I've done this with which classes. I think I only got to it with one or another. So I just wanted to show this to you, but I'm going to be up here. You, come with me. Hi. Let's go to this board. You're famous. Okay, good. All right. Have you heard of the step function? If you haven't, write this down. And if you can't see, can you guys see at home? Man, you have to get like super close. So I know you can see that. I will try to write nicely. So this says step function. Have you heard of it? Yes, no? No? Okay, good. All right, so there's a kind of function that is really cool. I really like it. It's called the step function, but it's got another name. It's called the greatest integer function. So step function, aka the greatest integer function. And if you broke into Greatest Showman show tunes right now, I wouldn't blame you. But the greatest integer function, the reason it's called a step function, I'm going to show you in a second, okay? But I want to give it a notation first. F of x, or whatever you want to call it. Okay, so you've got what kind of looks like absolute value bars with the x inside. But at the bottom of each bar, okay, so you got these two lines coming down like this. What's going to happen is it's going to look like, instead of like this, it's going to look like this. Like kind of two L's, one going the right way, one going the wrong way, facing one another. Okay, so it looks like this. And they're not super long. Okay, this one is, it's got so many names. It's also called the floor function. I don't care which one you call it. But kind of, it looks like we drew in a little floor, like a little step there. Okay. But the idea of this function is that if I drop in a number, 1.5, let's say, so the result right here, it's a weird way to say this, but it's what's called the greatest integer. It is the greatest integer less than or equal to whatever your number is. Greatest meaning biggest, largest. The greatest integer that is no bigger than this number. So you go to 1.5 and you say, okay, I want the biggest integer on that side. Oh, I already did that. I was going to bring them to you. But you're the best though, Sigmund. Thanks. Love you. See ya. Now we got extra. The greatest integer on this side on the number line. So, right? Here's, let's say, 1.5. What is the largest integer less than or equal to that number? Whatever that digit is right there. Whatever that leading digit is. F of pi. Okay, so the greatest integer less than or equal to pi. 3. Okay. Now there's a lot of x's that I could put in here that can give me 1. 1.1, 1.2, 1.3, 1.4, 1.7, 1.932, whatever. But what about like f of 1? What is the greatest integer less than or equal to 1? Less than or equal to the number 1 as well. So really, it's just whatever that number is, whatever that first, like on the left side of the decimal. Okay. Now, why do they call it the greatest integer? Or the floor? I mean, you kind of get a sense for why it's called the floor function. Like, you're sitting at that point. I just want kind of what's underneath it, which is just the kind of the integer. Check this out. Take out your calculators if you've got them, because I want you to press the same buttons as me. I will share my screen here for those of you at home, so you can at least get the best look that you can. And then we'll be done. Now, if you don't have a graphing calculator, it kind of puts you at a little bit of a disadvantage, okay? Now, I have to do this lesson again during fourth. I'm not going to make all those, I'm not going to retype all that. I'm just going to go to X or Y5 and type it in. Okay, so the greatest integer function, also known as the step function, It's obviously not going to be sitting here on the front because we don't use it very much. But the folder that we do use the most, right, is going to be, whoa, it's going to be our math folder. So jump into math, go right there. Okay. And we're going to scroll over to number. So press the right arrow once. And there it is. Option number 5, int for integer. Okay, greatest integer function. Okay. And I just want x. For now, just plain old x. Now, so we all get the same picture. Let's zoom decimal, the cool one that I showed you before that I really like because it's already squared out. I love it. So zoom number 4. What does that kind of look like? Steps, right? Mathematicians were not super creative sometimes when it comes to names. It's like a set of staircase. Okay, and that's the idea. Is that okay? So from between 0 and all the way almost to 1. What number am I going to get back? 0.5, 0.7, 0.8, 0.9, 0.99, 0.99999999999. The greatest integer less than or equal to all of those numbers is just 0, which is why the y value that's coming out is just 0. But the moment we get to actually 1, now I actually get to 1. And then 1.5 and 1.7 and 1.9 and 1.999 and all of those until I actually get to 2, we're just going to spit out 1. And then I get to 2 and it starts to happen. So it really kind of looks like this. Right, close circle at that spot, but then open circle at the end, all the way down, and it just goes on forever and ever and ever. Okay, so that's the greatest integer function, the step function, the floor function. There's a ceiling function as well that just takes the smallest integer greater than or equal to, so it just kind of slides these up one spot. Okay, not super critical to your calculus success, because there's all these breaks and gaps, and we don't love those as much as we love continuous functions. But I just wanted to show it to you so you see it, okay? Think of it like you pull into a parking garage, and it costs you $2 for the first half hour, and then $5 for the first hour, and then $15 for like 3 hours through 6 hours or whatever it is. That's the kind of graph that you would see. Because it doesn't matter, like these like long time frames, same cost. But the moment you get to this next spot, boom, now the cost goes up. Okay, so step functions work really well for actual real life kind of scenarios. That's it. That's what I wanted to show you. A little step function action. Okay, 1.3 done. And guess what? Chapter 1 done. That's it. It's enough. Okay. Like I said, 1.4 is transformations. 1.5 combinations. 1.6 inverses. I trust that that's all relatively familiar to you. It will not show up on a chapter 1 test, but I do believe that you know it. Okay, so I can just talk about it, just like we did today with moving things up and down. Okay, so what does that mean for the rest of the week? Okay, what I'm thinking about for Thursday, and for the folks at home, I'm thinking about this for you for Wednesday, is just a nice practice day. I'm going to just come up with a whole bunch of practice ones of all the kinds of things that we've done, the kinds of things you can expect to see whenever we decide to take a chapter 1 test, however it looks, and so you're ready to go. Okay. I do want to give you a little bit of symmetry practice though tonight. Okay. For cohort A, that's for tomorrow, so make sure you get that done if you get a chance to. And then for you guys, that's for Thursday. Okay. This way, when you walk in the door on Thursday, we can say, yep, I got symmetry. I feel really good about it. Here we go. I can do the graphical side, but way more importantly, the algebraic side. But the visual stuff, of course, is good too. And then I think we'll talk Thursday about what we think we want to do. How am I going to test you in a way where you're doing it honestly and everybody's getting a fair shot to get the grade that they deserve and the grade that they want? So have some ideas when you walk in the door as to how you think that could work, whether it starts Friday or next week. See ya. Folks at home, all good? Any questions? Again, drop your name in the chat if you have not had the chance to. I need to write them down. And then I'm going to stop recording. Hi, what's up?
I just wanted to talk to you, let you know like what's going on with my mother and stuff.
Okay.
So they're getting better, and like for a while I was getting like last year contacts on. I was
Yeah.
getting like a nice set,
Okay.
And sometimes they're on the box now, so every week they get self-injections.
Okay.
And then they're gonna see how that goes.
Okay.
I might try something else.
Good.
Getting better and like.
Awesome. Okay. Well, I'm glad to hear that we have progress, right? That's so important. So you feeling better is obviously the most important thing. But keep me in the loop as things happen, and if things change, or if there's, like, if you need the lights to be shut off, or if you need